Welcome back, everybody. This is part 2 of our series on vector fields, the calculus of vector fields. Part 1, we focused on just how to draw a vector field, what it was, and now we're going to work with a little bit of calculus. Today is going to be a lot of concept day. It's going to be a lot of talking about different introducing some new ideas about vector fields and kind of just showing you how to do them. The applications will come a little bit later, so be patient with me, but there's a lot of new things to learn here. All right, well, one of the things that we need to realize is that we've already studied one type of vector field, all right, and that was the gradient. Remember, del F. All right, so let's review just for a second on what a gradient is. So if I say f of xy equals x squared y minus y cubed, and I said find the gradient, all right, why don't you pause the video real quick, find the gradient, and we'll talk more on the back end. All right, hopefully you started with our partial with respect to x and our partial with respect to y. I have a 2xy for my partial with respect to x. And for my partial with respect to y, I have x squared minus 3y squared. So we can put that together as del f of xy equals 2xyi plus x squared minus 3y squared j. And that is indeed a vector field. So what we find here is that if the vector field is the gradient, then the vector field is called conservative. All right, so this is a conservative vector field. All right, so if I asked you to, let's say here, let me give you a quick example. If I asked you to find the conservative vector field, for the function f of x, y, z, got to give you a z in there, equals y ln x plus z. All right, why don't you pause the video now and try to find that conservative vector field, and we'll talk about the answer on the back end. All right, hopefully you worked it out. I got my del f of x, y, z equals, I got y over x plus z in the I direction plus ln of x plus z j plus y over x plus z in the k direction. So this is the gradient. Now, if you have any trouble with the gradient or need some reinforcement, I would encourage you to go back to the video dealing with gradient. All right, but this is a very straightforward question I can now give you. Instead of saying find the gradient, I could say find the conservative vector field, and you would know that you are finding indeed the gradient. But what if I gave you a vector field and I wanted you to tell me if it was conservative or not? All right, there is a test for a conservative vector field. All right, and that test says let m and n have continuous partial derivatives on R. The vector field mi plus nj is conservative IFF means if and only if the partial of n with respect to x equals the partial of m with respect to y. So if I gave you a vector field, this is how you would tell me if it was conservative. So here's the next example. Decide whether the vector field is conservative. And here's your vector field x squared y in the I direction plus xy in the j direction. All right. So I need my partial of m. That's a terrible m. I'll make a better one. With respect to y, and I need my partial of n with respect to x. All right, so why don't you pause the video, do those two partial derivatives, and we'll talk on the back end. All right, so if you do remember, according to the definition, here is m, all right, and here is n, all right. So if I'm doing my partial of m with respect to y, that means I want my d, right, my derivative with respect to y of x squared y, which equals just plain old x squared. And my partial of n with respect to x is going to be xy, right? So my derivative, partial derivative would just be plain old y. So the answer would be no, it is not conservative. All right, let's try one more. So if I say I have f of x y equals 2x I plus yj, I need my partial of m with respect to y, my partial of n with respect to x. Why don't you do those two partial derivatives again, and we'll talk on the back end. All right, if you did those two partial derivatives, you should get 0 for both of them. So the answer would be yes, the vector field is indeed conservative. Okay, the next thing we're going to talk about quickly is the curl. All right, and the curl of xyz equals, right? plus pk. So I'm using 1 in space now. Equals the gradient cross my potential function. All right. Now, with a vector field in space, remember this is a cross product. If you need further reinforcement with the cross product, go back to the video dealing with cross product. But this is going to equal partial of p with respect to x minus partial of m with respect to z, and then that's in the j, plus partial of n with respect to x, partial of m with respect to y in the k direction. This seems like an awful lot, but I'm going to show you that it really isn't. If the curl of f equals 0, then f is irrotational. That will become significant a little bit later in the lesson. All right, so let's get to one of our examples. All right, so here it is. There's your potential function. There's your vector field, 2xy in the I direction, x squared plus z squared in the j direction, 2yz in the k direction. So we need our gradient cross our potential function. All right. So rather than memorize everything I just gave you in the definition, I would suggest you do the cross product the way we did them when we did vector fields, or when we did vectors, excuse me, where I had I, j, and k. Now my gradient means we need the partial derivatives of each one of those, right? So I'm going to have my partial with respect to x, my partial with respect to y, my partial with respect to z, and then my 2xy, x squared plus z squared, and 2yz. And I'm going to put that in a big old determinant. And now let's piece it out. So in my, that's going to equal, let's make the 2 by 2 determinants. So I'm going to cover up the I column, right? The first row, first column. And I get my partial of y, my partial with respect to z, x squared plus z squared, and 2yz, I, minus my partial with respect to x, partial with respect to z, 2xy plus 2yz j. And remember the sign switch, so it's a plus over here. And I need to cover up the top row and final column. So I wind up with my partial with respect to x, my partial with respect to y, and 2xy x squared plus z squared in the k direction. Now remember, your cross product is going to yield you back a vector. So at this point, I want you to pause the video, work out the determinants, and then we will talk about the answer on the back end. All right, so I got 2z minus 2z I minus 0 j plus 2x minus 2x in the k direction, and when I work all of them out, I get just 0. 0i, 0j, 0k. So the curl of f equals 0, which means that f is indeed irrotational. You might ask, why do I need to know the curl? Well, I'll give you one reason right now. It's because if you wanted to test a vector field in space, right, for being conservative, all right, and that would be something like f of x, y, z equals mi plus nj plus pk, right? You could say it is conservative if the curl of f equals 0. And that is by far the much easier way to test a conservative vector, to test a vector field in space for being conservative or not. All right, the last thing I want to talk about is divergence. So the divergence of a vector field. And divergence could have applications in a variety of places. So I at least want you to hear the term and know how to get it. All right. So the definition would be that the divergence of f of xy, which equals mi plus nj, is, and this is how you write it, div equals my gradient dot my function. So that would also equal my partial of m with respect to x plus my partial of n with respect to y. All right, now remember, our dot product yields us back a scalar. All right. So what if we wanted a vector field in space? What if we wanted f of x, y, z, that would equal mi plus nj plus pk. And we would do the same exact thing. The divergence of f of x, y, z equals my gradient dot my vector. So, which would be my partial of m with respect to x my partial of n with respect to y, my partial of p with respect to z. All right, and if the divergence of f equals 0, then it is divergence free. All right, so let's do one last example regarding divergence, because I want to show you how this will yield back a scalar. So find the divergence at 2, 1, negative 1 for the vector field f of x, y, z equals x cubed y squared z I plus x squared z j. All right. So I need my partial with respect to x, partial with respect to y, partial with respect to z. Excuse me, I also have plus x squared y k. So my partial with respect to x of x cubed y squared z plus my partial with respect to y of x squared z plus my partial with respect to z of x squared y. All right, so why don't you pause the video, do those partial derivatives, all right, and at the same time, why don't you insert your point, because you're going to do those partial derivatives, insert the point, and you should get out a single number, and let's see what it is. All right, hopefully you did your partial derivatives okay. I got, sorry about that. Three x squared y squared z. Now my second partial is with respect to y, but there's no y's in it, so that's plus 0. My third partial is with respect to z, but there's no z's in it, so that is also plus 0. So when I insert 2, 1, and negative 1, in for x, y, and z, I got negative 12. So that would be my divergence. All right, would be negative 12. All right, there's, this is just kind of a start. I'm introducing you to some concepts, talking to you about how to do them. We're going to see some of the these concepts be applied in later sections. There's a lot more practice to do, but thank you for listening.